Welcome to Lecture 10C, entitled Double Integrals over General Regions. And this involves basically symmetry. In other words, how can we exploit a symmetry in a problem? Now, there are problems in the textbook that deal with symmetry, and we discussed examples in the previous lecture. However, the material in this particular lecture is not in the textbook, and it deals more with the mathematical derivation, which allows you to know whether or not you're dealing with a problem which involves symmetry. And so to some extent, if you're in a hurry, there's no need to look at this lecture. But if you're interested a little bit more in terms of how do we basically mathematically describe symmetry when we're dealing with double integrals, then you by all means can watch this video. So as usual, the second slide is just a summary of the contents of this lecture. It's a relatively short lecture. So the first thing we'll do is just look at symmetry for one variable case, which would be a review of last year. And then we extend that to the two variable case. All right, so we're going to start with the single variable case, and we're going to try to sort of come up with some general rules regarding how to simplify an integral. In this case, it's a single integral. So let's say you have an integral between an upper bound and a lower bound, which are the same except one is the negative of the other. And what we can do is we can break the integral into two parts, from minus a to 0 and from 0 to a. We can also basically play a trick where we just say that we're going to swap the order. So instead of going from minus a to 0, we're going to go from 0 to minus a, in which case we end up with a negative sign out here. The reason I do this is because the process to follow makes it easier to work with this formulation. So this is basically what we end up with, this term here. So the next step is to consider a change of variables for the first integral on the right-hand side, which is this one. And normally what we would do is we use dummy variables, but this is a relatively straightforward procedure. So I'm just going to say let x be equal to minus x. So if x is minus x, this becomes a minus. Dx will have a negative sign, and the limits will change sign. So this will go to a. So if you look here, this term, minus from 0 to minus a fx dx, the minus sign is because dx becomes minus dx, so that negates the minus. This becomes minus x, and the minus a becomes positive a. So this basically is equivalent to this if we let x equal to minus x. All right, so we're going to now replace this term by this instead, and so we end up with the expression that you see here. So this is 0 to a f minus x dx plus 0 to a fx dx. We can put them together and we end up with this expression here. So now the question is, all right, can we sort of impose some type of symmetry on the problem? And so one example is if f of x equals to f minus x, fx, then this is an even function. So for example, this would be an even function. You'll notice this side is the same as this side, the same value y independent of x being positive or negative. In that case, basically, in this function here, these two basically will be the same. And so that's like just taking twice times the integral of one of them. On the other hand, if they're odd, then these two will cancel out and you'll get 0. So for example, y equals x would be odd. So now let's extend this to the multivariable case. In the multivariable case, we're talking about a region, and a region has 4 quadrants. And so if we want to break this up into a number of quadrant integrals, then a to minus a, you could show this to be from minus a to 0 plus from 0 to a. All right, so that's 2. And then minus b and b would have to go from minus b to 0 and 0 to b. And you'll end up with basically 4 different combinations to consider. So this one would represent integration over the third quadrant. This is the fourth quadrant. This is the second quadrant. This is the first quadrant. So now what I'm going to do is consider a change of variables for the first and third integral. This one and this one on the right-hand side. We're going to let x equals minus x. So a similar pattern is what we did on the previous slide. Then what happens is that these two terms get transformed into these two terms. So there's the minus x, there's the minus x. You'll notice basically in this case the term 0 to a basically, this minus a right? This minus a becomes a positive a. And if you raise it on the top, you have minus. But because of the dx equals minus dx, everything ends up being positive. And so this here now is a replacement for these two. So we take these now and substitute back into the original equation. So now we end up with this expression here. All right, so next we do is recombine the integrals. All right, if we recombine it, you'll notice basically you have 0 to a, you have a minus b to 0, and you have a positive b to 0. All right, and so we basically combine them, and so we'll end up with a minus b to positive b and a 0 to a. They are all common 0 a's, but there's a minus b here, and a b here, and b here, so they come combined into form a double integral with two terms, fxy plus f minus xy, dx dy. So all the figures to follow, basically you can access at this link if you wish. Click on them so you can play with them and look at them from different points of view. All right, so let's look at specific cases. Let fxy equals f minus xy, which is an even function of x. All right, in that case, basically, these two are identical, so this can be written as 2 times fxy, this integral. On the other hand, if it's odd, then this is the minus of this, then these two subtract and you'll get 0. So here's an example of even function of x. X squared means function remains the same whether x is positive or minus. In this case, of course, it reverses sign depending on whether x is positive or x is negative. So this is an odd function in x. This is an even function of x. All right, so let's look at another example, but in this case, we're going to basically let y equals minus y. So in this case, we'll be dealing with the third and fourth quadrants, and it'll be the first and second integral. All right, so we're going to replace in these two here, we're going to take y and make it equal to minus y, which means dy becomes minus dy. And the integral for y, which would be minus b and 0, this would just become a positive b instead of negative b. And so this term will translate into this term, and this term will translate into this term. So we substitute now, instead of putting these back, we take these and substitute for these two, put it back in the original expression, and we end up with this expression here. Again, combining integrals. So in this case, what we see is that the minus a, 0 to b is common to all, 0 to b, 0 to b, 0 to b, 0 to b. But you have a minus a here, you have a minus a here, a positive a here, and a. Combining, we end up with this integral that you see here. So this is the case for y equals minus y. All right, so let's look at different cases. If fxy equals fx minus y, that means we have an even function of y. Then this basically just becomes twice this, right? Because this just gives two contributions. If it's negative, that's an odd function of y, then of course this will become 0. And again, here are some examples. Here's a case for y being even, and this is a case for y being odd. All right, let's take another case. Let's say if x is minus x and y equals minus y. In this case, basically, we'd be looking at the third. We're going to look at the first and second integral, the third and fourth quadrant. And so we basically will take these two here, right, and make the substitutions x minus x, y minus y. In this case, both integrals, limits, will change sign. But you've got a negative contribution for dx and a negative contribution for dy, so the multiplication of two negatives will be a positive. And so this one transforms this way, and this one transforms this way. So we substitute back into the original expression. So these two terms are now replaced by these two, but we retain the last two, which are the ones you see here, add them together, and combine the integrals. So in this case, you'll notice that you've got 0, you've got b is common to all, but you have a positive a minus a positive a, and a minus a. So when you combine the two, you'll end up with an expression from minus a to a, from 0 to b, of this. So we just say then, let's say if fxy equals f minus x minus y, then again we'll get a double contribution. If fxy equals minus f minus x minus y, and this will be equal to 0. So here's some examples to show this specific case where fxy equals f minus x minus y and fxy is minus f minus x minus y. In this case, we can't use the words even and odd. They have no specific meaning. So we just leave it as is. But here are the functions for you to look at that basically have the properties as indicated above. All right, so the last situation or case we're going to consider, in terms of dealing with exploiting symmetry and multivariable integration with two variables, is the case where multiple conditions can occur. So I've written it out at the top again, that we can break out the double integral in terms of 4 individual quadrants. And I'm going to consider two cases, a case 1 and a case 2, which are basically shown sort of in a table format. And the color coding here is such that these things basically allow you to go through this rather dense slide. So the blues are all basically related to each other, yellows are related to each other, and so on. So let's look at the first case that we're going to consider. We're going to essentially say if fxy equals fx minus y, which means even y, and logical and fxy equals f minus xy, which means even x, right? If both conditions are satisfied, then we can essentially state that fxy is equal to f minus x minus y. Now that has no name to it. It's just a basic inference. And how do we know that? Well, if we basically take the second expression here and substitute for minus y, then this becomes fx minus y equals f minus x minus y. But fx minus y equals fxy. Therefore, we can make this assertion here. Okay, so let's then carry through. We know that. We know from the previous results for even x that this expression is equivalent to this expression. You can go back and review the case if you wish. I'm just stating basically what's already been described before. However, we can take this and break it up. We can break it up so that we go from minus b to 0 and 0 to b, which means that we've broken it up in this fashion here. And then this particular term here basically, right, is equal to this for even y, okay? And given that we've had both even y and even x, we can now basically make this additional statement. So that means that original expression now, the green can be replaced by the yellow, and we just carry forward this term here. But if you look at this, essentially the limits on this and the limits on this are identical, so they can all be grouped under one common, as one common argument. And here are all the 4 terms. But we've already said that we have even x, even y, and also we have that this condition is satisfied, which means each one of these is equal, which means I could basically say it's 4 times integral between 0a on the integral and 0 and b on the outer integral. So that basically is the conclusion. It makes life easy in that if these conditions are satisfied, you just need to integrate over one quadrant and multiply the result by 4. All right, the second case basically is if fxy equals minus fx minus y, which means odd, or this one is odd, either case, then this is equal to 0 from a previous case, and this is also equal to 0 from a previous case. All right, so let's take the specific examples, take 2 cases. So we know, for instance, this case 1 condition will allow us to do this calculation. And this is an example to illustrate when we have even y and even x, this particular function. If you look at this, you can clearly see that every quadrant looks identical. So you can just integrate over one quadrant, one region, and multiply by 4 to get the result. If you look at this result here, say for 1/5 x cubed y, x is odd and y is odd. So in this case, if you were to integrate over the region, you would get 0 no matter what. All right, so that concludes Lecture 10C. Thank you for listening.